Okay, yes, sorry about that. I accidentally closed Zoom, I guess. All right, so on page, at least in my book, I have an older edition, which is the 7th edition, I believe, but on page 176, 177, I get a definition for dH, which is C sub P as a function of T dt. So I can make that substitution, right? ds is equal to C sub P as a function of T dt. Not sure what happened here. Okay. And then we know for an ideal gas or small temperature changes, or sorry, not for an ideal gas, but you can say for small temperature changes, C sub P is constant, right? So now we have ds is equal to C sub P, and I put a dt on here, but it's actually this dt over T. All right, we can integrate from state 1 to 2 on both. So we get S2 minus S1 is equal to C sub P ln. And then I'm going to make, ln of 1 over T. And let me just do, from state 1 to 2, state 1 to 2, right? So yeah, you'd have ln of T2 minus ln of 1 over T1, right? Okay, so now I won't go further here, but now you can do some algebra here, and you can get T as a function of S, right? And you might have to play around with these T1s and T2s a little bit. But essentially you would get that it's an exponential curve, right? Because you have this ln in here. And you're going to see that to get the T's out, you're going to have to take E, raise it by ln to cancel on both, and then raise it on the other side. So you're going to get an exponential curve, right? So that's another Dr. Jones question. Okay, let's see. Okay, yeah, so we went over first law, second law, work interactions, irreversibilities. We went over have to reject heat. We have to plug in the refrigerator, right? So again, have to reject heat. That's why the example problem I gave you didn't work. And that was the point, is that you were supposed to realize that you cannot have a heat engine that does not reject heat, right? You always have to reject heat. Okay, Gibbs equations, the canonical equation. Let's see. Okay, now we might go over thermodynamics. I might have property relationships here. And at least for now, I'm going to have pressure, temperature, enthalpy, entropy, internal energy, specific volume. And it's important to realize that this is just density raised to the -1. If you end up having to use a density term, you can convert that to specific volume, and then quality, right? This one is only valid underneath vapor dome. Okay. And then, sorry, let me actually erase that. And then to calculate quality, I notice I don't remember, in the book, there's a definition where quality X is equal to V average minus VF over VFG, right? If you end up having to calculate quality, right? And actually you can use any property here. As long as VF and VFG, sorry, just subscript. Okay, property as long as F and FG is known. So you could use internal energy, you could use entropy, you could use specific volume. Okay, so this V average is given in problem, or sorry, I guess maybe I should say representative of the system. And VF and VFG are table values. Okay. Okay, and then with this, you could do state postulate, right? To independent intensive properties fixed state. Okay, so it's really important. I think everyone pretty much understands intensive, so it's mass independent, right? Obviously, volume depends on mass, but specific volume doesn't. But I would really focus on independent. And what does that mean, right? So what it means is that pressure and temperature under vapor dome are not independent. Okay, and to give you an example of that, I would give you an example would be like, I give you a cup of H2O at 1 atmosphere and 100 degrees Celsius. Is it a gas or is it a liquid? And the correct answer is you don't know, right? Because we know that at 100 degrees C and 1 atmosphere, water boils, right? But we don't know how much of it boiled, okay? But if I gave you a cup of H2O at 1 atmosphere and 60 degrees C, you could without a doubt tell me what phase it's in. It's in the liquid phase, right? So that's maybe kind of a real world example. So really any combination of these properties that we wrote down, all of them except for pressure and temperature are always going to be independent. And at least with the stuff that you're dealing in this class, right? And so the only ones you have to watch out for is if you know a pressure and a temperature, you have to make sure you are outside of the vapor dome in order to use those. If not, you have to find a different property in order to fix the state of the system. Okay. There's other things, you might do, let's see, you might have concepts here. So you might have adiabatic, which is like it's insulated is a keyword that they give in problems. But what it means is or no heat transfer. Q dot. Okay, another one might be isothermal. Which is temperature remains constant. Right? But isothermal is not the same as adiabatic. right? Because adiabatic implies no heat transfer. So if you have a gas, like in the Carnot cycle, I believe a part of it is isothermal, the cycle, a part of the cycle is, right? So if you have something like that, right? So you imagine a gas expanding. We know when gases expand, they cool off, right? They cool down. So if you have an expanding gas that's isothermal, then that means you're adding heat to it. And if you're adding heat to it, that means it's not adiabatic, right? So this is something that confused me in the beginning of thermodynamics, I remember, is adiabatic and isothermal, because, typically we think, if you have your mac and cheese or whatever, and your mac and cheese is isothermal, you think, oh, it's just staying at one temperature, right? So there's no heat transfer. Well, actually, there is heat transfer, right? You have some convection coming off the mac and cheese, so you'd have to be putting heat back into it. I don't know. It's maybe a silly example, but I just want you to understand that adiabatic and isothermal are not the same thing. Adiabatic implies, or adiabatic is no heat transfer. An isothermal case could be no heat transfer. It could be adiabatic, but it is not definite that it is adiabatic. Okay. Yeah, so you could have another one where, let's see, where I might put this. So you could have, I don't know, maybe another one that is like approximations, right? And obviously we've already made some approximations, so you would want to add those here. I'm not going to, but one might be ideal gas, right? And then if something is ideal gas, you have C sub P, C sub V, U is only a function of temperature, H is only a function of temperature, right? We know PV is equal to RT. Okay, now how do we know if something is an ideal gas, right? So we used reduced pressure and reduced temperature. Okay, so then you'd say if P reduced is equal to P over P critical, and that is less than 0.1, then ideal gas. Or, and I'd like to just point out or, right? We know T reduced is equal to T over T critical. If that is greater than 2, then ideal gas. So only one of these has to be true. So the idea is calculate these values, right? Where these are given, right? And these are lookup values. Table A1, right? So you can also then use compressibility chart, right? So we know Z is equal to PV over RT, right? So use T critical or T reduced and P reduced to find Z. And then you could use the ideal gas law, knowing that PV is equal to ZRT, right? Okay, and that chart was something that looked like this, right? Where it had some lines coming up like this. Let me see if I wrote that down. In my book, it's introduced on page 138, so it should be close to that in your book. Yep, in 3.7. So this is 3-7 in your book, right? And so that one gives you T reduced, but the one in the back of the book, which is near table A15, I believe. Let me just double check on that. Yeah, figure A15. This one gives both pressures and reduced temperatures. Right, so, yep. Okay. Yeah, so like this one would be T reduced is equal to 2. And then this one would be T reduced is equal to 1. Right, so you would find, and then this x-axis is your P reduced. So you would, if you want to use compressibility charts, you do both, right? So you find your reduced temperature and you look up that line, right? So let's say if it was 1, right? And then your P reduced was here, that would give you your Z factor, I don't know, 0.1 or something, right? So that would tell you it's 10% like an ideal gas, right? And so that's the correction coefficient to the ideal gas law. I don't recall using compressibility charts all that much, but these things that are highlighted here about the reduced pressure and the reduced temperature are pretty important because, you know, a test question might be, under these conditions in this cycle, can it be considered an ideal gas, right? And then you'd have to prove it. And this is how you would prove that it can be approximated as an ideal gas, right? Yeah, and then I think the biggest other, the other thing is just the diagrams, right? So okay, so you have TS and PV diagrams. You have more than that, so I'd suggest studying all of them, but the main ones are TS and PV, right? And then for this, like your TS diagram might look something like this, right? So anything in here is liquid vapor mixture. This is superheated vapor. This over here is ideal gas. And over here is compressed liquid. Right? So underneath the vapor dome, I would use X from properties. And essentially what X here, wait, so just a second, let me. Just do that. Okay, so this is X equals 1. This is X equals 0. So so again, this is only valid under vapor dome because it's just telling you which point you're on, right? So if your quality is X, if your X is 0, then you're right on the line, right? So technically you're still a compressed liquid. Or sorry, not a compressed liquid, you're a saturated liquid. And then anywhere on this line, you're a saturated liquid vapor mixture. And then on this point on the right side, you've become a saturated vapor. And then after that, any other temperature entropy increases is a superheated vapor. And then much greater than that is you'll be able to consider it to be an ideal gas. Okay, so I think, let me just look at my list of things that I wanted to cover. Yes, I've covered basically everything that I wanted to cover. Okay, so I know it's kind of messy and freehand and everything, and I apologize I didn't have more time to put something together a little bit more organized and better for you, but I will try and post this as an example for you to look at. This is not exactly how I would do it. I would definitely come back and spend some time on this to make it more organized, but this is kind of a rough idea of important concepts for the class, right? And it's essentially on one page. I know it looks like a lot, so let's just go over it one more time, right? So choose a system, draw the interactions, use basic concepts and fundamental laws. I promise that you'll be able to convince Dr. Jones you earn more points by doing that. Okay, first law. Okay, went through the derivation, but essentially this is the full form of the first law, right? Something that you might add here is just up here. dm dt is equal to m dot I minus m dot e. Okay, when steady, it equals 0. Okay. Thus, m dot I is equal to m dot e, which is just equal to m dot. Okay. So when you haven't covered transient problems yet, which is they're not steady. So I'm not really going to cover transient, but steady is when this dt term is the d dt is equal to 0. Right? So same thing here. I can consider, so here I'd say steady or transient, right? But you haven't covered transient yet. Okay, so thus 0. Okay, so we said our internal energy can be changed through heat, work, and mass interactions. If it's a closed system, we take out the mass interactions. Heat is probably relatively easy to know if it's there. And then work, we have these three terms right here, right? Do we have boundary work, right? Where this be the integral of PdV, right? So then are there any electrical wires crossing the boundary? Are there any shafts crossing the boundary, right? And that tells you if there's any work interactions. Then we came over and we said, okay, well, let's talk about our second law. So we have the change in entropy with regards to time is equal to this equation here, right? And we can use first law here if we need to. Okay, S dot gen, this is where we talked about irreversibility. So we talked about the 7 irreversibilities that can occur, and then we highlighted in green the ones that are important to this class: electricity, unrestrained expansion, meaning no piston, as well as heat transfer through a finite temperature difference. And then I pointed out very strongly that if these definitions here in red, where if it's externally reversible, all of these irreversibilities in green are happening inside the dotted line. Internally reversible is that all the green happens outside the dotted line. Totally reversible is there's just plain no irreversibilities, not in the systems, not in the surroundings. Okay, and this is important because this tells you if you have S gen or not. If you have an internally reversible system, your S dot gen is equal to 0, like you chose that system, right? So make sure that any of these green things are inside the dotted line if Dr. Jones asks you to calculate S dot gen, right? So in big red, I wrote, do not choose internally reversible system here. And that's if Dr. Jones asks you to calculate S dot gen, because otherwise it's the logical fallacy that we talked about, right? Okay, we talked about the Kelvin-Planck statement and the Clausius statement, where the Kelvin-Planck is that you have to reject heat, right? So if you have a system on the test that does not reject heat, then you should definitely say this violates the Kelvin-Planck statement. And then the Clausius statement is plug in the refrigerator, right? The refrigerator doesn't work by itself. You have to put some work into the refrigerator in order to move energy from a low temperature reservoir to a high temperature reservoir. Okay, right at the end, we briefly talked about diagrams with TS, PV, and kind of understanding the points where you have a compressed liquid on the left, you have saturated liquid on the left point, saturated liquid vapor mixture on the line underneath the vapor dome. On the right point, you have a saturated vapor. Outside the line, you have a superheated vapor, and then outside the superheated vapor, you have the ideal gas, right? And speaking of ideal gas, we came over here, and this was one of the approximations we made. We said, okay, so for an ideal gas, the internal energy as well as the Enthalpy, they're both only functions of temperature. We have the ideal gas law, PV equals RT. We know C sub P, C sub V are constants. For reduced pressure, reduced temperature, this is kind of when can you assume something is an ideal gas? Air is, unless you're given some extreme conditions, air is almost always considered an ideal gas in this class. But you know, if you have a superheated vapor of refrigerant or something, you do not want to use the ideal gas law unless the reduced pressure or the reduced temperature are true, right? We talked about using the compressibility charts if you need to. The Z is essentially just to use the compressibility chart to find Z, and then you include Z in your PV equals ZRT now. For an ideal gas, Z is equal to 1, which makes that relationship true. And it's essentially just a correction coefficient so that you can use that equation. Okay, we talked about like those 7 properties of thermodynamics, and we talked about how to calculate quality here. The state postulate, 2 independent intensive properties. So again, that's where we talked about, you know, I give you some H2 at 1 atmosphere as well as 100 degrees C. What state is it in? You can't tell me because pressure and temperature are not independent underneath the vapor dome. We also talked about what adiabatic and isothermal means. And we also talked about Gibbs equation and how to derive maybe some formulas if Dr. Jones asks you to do formulas. So yes, again, I know it's a lot. And I think here it maybe looks a lot more than it actually is because it's not super organized. It is somewhat organized, right? But you should find out a system that works for you. I would highly recommend doing at least like a 1-page summary of these concepts and at least put, you know, you could just put page numbers by them or something just to help you be more efficient in your exam. So anyways, I hope you guys have a great President's Day. Hope you do extremely well on your exam. Again, you know, if you don't, I just encourage you to be neat. Do the steps we talked about. Also, don't erase any work, because if you get to some point and you realize, hey, I chose the wrong system, I should choose another system because the system isn't helping me, leave that. And then just write a sentence. You know, I realized the system wasn't helping me for this reason, so I'm going to choose this system instead, right? And then that way, you know, if you don't get the score you like and you go in and are arguing about how you mastered course outcomes and deserve more points, that is a big win for you, because Dr. Jones he's pretty heavy on recognizing when you're wrong and being able to correct that, right? So don't erase it, just leave it and say, I realized I was wrong because of this, I'm going to do something different. And I promise you that will help you in when you're asking for more, you know, demonstrating that you deserve more points. So anyways, have a great exam, as great of an exam as is possible, I guess. And hope to see you around. Goodbye.